So anyway, this morning I had plenty of time to set up and everything was all nice. I went full Relief Society. I had a tablecloth. I had a little Hummel decoration. So, but because there's a class in here right before our class, I was kind of scrambling. These cookies are from Nuremberg, Germany. And many, many years ago, before most of you were born, I served in Nuremberg. And it turned out that our apartment, our missionary apartment, was very close to the factory where they made these cookies. And my companion and I made two very important discoveries. And the first discovery was that if you went to the factory, you could buy a big bag just filled with broken cookies for dirt cheap, just a couple of marks. And the second discovery we made was that broken cookies tasted just as good as unbroken cookies. And so I found these in the bookstore and immediately bought pretty much everything they had. I bought 85 packages, and when I left, there were 3 packages left. So if you're looking for Lebkuchen at the bookstore, you might want to go somewhere else. The reason I brought them is that, especially this time of the semester, we were feeling a lot of pressure. Everything just kind of coming down on you at once. And a lot of times we can feel broken. And I want you to know that all of us are broken. As Sister Craig said at a women's conference, Jesus Christ heals broken things. We are all broken in some way. Broken hearts, broken dreams, broken bodies, broken minds. And that is okay. Jesus Christ welcomes us in our brokenness and in our desire to become his disciples. I just want you to know that if you're feeling overwhelmed, you're not alone, and you don't have to deal with it alone. And if things don't go well in your exams, your parents still love you, and I still love you. Okay, and more importantly, our Heavenly Father loves us just as much when we're broken as if we weren't broken. So enjoy the cookie and maybe break it. So, would someone be willing to give us an opening prayer before we get started on physics? Thank you so much.
Heavenly Father, we're so grateful for the opportunity to study here at BYU. Father, we're grateful for our professor, and please bless him. Grateful, Heavenly Father, to study physics this semester, and please bless Heavenly Father in this class, be able to have clear minds, be able to understand the things that we're learning. Father, we're so grateful for this Christmas season to celebrate the birth of thy Son, Jesus Christ. Grateful for the atonement of Jesus Christ, and we say these things humbly in the name of thy Son, Jesus Christ. Amen.
Amen.
Thank you. Okay. Wrong button. So, we just have a couple of topics left before you're ready to take that last exam. And remember, the last exam we call the final exam, but it's really just the 4th midterm, covering this new material on fluids and rotation. Today, on the last reading assignment, your score got changed last night at 9:30. I got an email from Dr. Benyon saying he really wanted everyone to take a quick survey. He's doing some research. He needed the data. And so wanting to support him, I changed that reading quiz that you get 2.5 points for doing the reading assignment, 2.5 points for doing the really quick quiz. Now, some of you had already taken the reading quiz and gotten your 5 points. Well, last night at 9:30, I regraded everything, so you ended up with 2.5 points. To get the other 2.5 points, you got to go in and take that it's a really easy quiz. You know, what's your favorite color? You know, do you like tacos? It's not hard, okay? It's mostly about that new testing approach where there's an A exam and a B exam, and whether you felt that helped in the course. Some announcements. Homework solutions are there at Max. I encourage you before you take that last exam to go through and make sure you understand the reasoning in those solutions. The exam preparation sheet is not only at Max, but it's up here. If you didn't get one on your way out. 2 practice exams and their solutions are at Max. And I just want to point out that at Montana State University, the final exam was mostly on the new material, but it was a little bit cumulative. And so there are problems on those sample exams that deal with earlier parts of the class. There won't be problems like that on your exam. So just ignore those problems when you're going through the sample exams, okay? I felt like a number of us are still struggling with buoyancy and with the torque idea. And so on Wednesday, I will be holding a review session here in this room, Wednesday evening at 7 o'clock. I will record that and post it to YouTube, send you out a link. But if you, and I'm not going to do anything scripted. I'm just going to show up and answer your questions. So if no one shows up, I'll go home. But if you show up, I'll answer any questions you have to help you get through. Okay? Questions about the exam? It's going to be open the entire finals period at the testing center. Okay, let's start by taking attendance. Okay, now you can click.
You got 5.
Okay, last call. Please get it done. Okay, we're here. Let's start with a quick review of torque. And I can't emphasize this enough. Torque is just a force times the distance to the pivot. But they got to be perpendicular to each other. Okay, and 95% of the time they are. In those 5% of the time when they aren't, we've got 3 separate ways that we can find that torque, and those are summarized on the back of your exam preparation sheet. And we'll practice some of those methods today. The big idea is one we've seen before, and that is that when something's in equilibrium, when it has 0 acceleration, things have to be balanced. And in a linear way, what that means is that all the force left has to balance all the force right. And all the force up has to balance all the force down. And when we drew our free body diagram, we just drew a dot because all we cared about was the motion of the center of mass. And that dot represented that center of mass. So if I balance all the force left with all the force right, I know that that unknown force has to be 250 newtons. It's that easy. Now, when things are rotating or not rotating, but could rotate, we can also say that because there's no angular acceleration, that's what alpha is, no angular acceleration, that means all the torque clockwise has to balance all the torque counterclockwise. Now, folks, technically, torques are either into the board or out of the board. And we could call one of those directions positive and one of those negative. But it's been my experience, long experience, that we have way too many minus signs in physics. And they get in the way. That's where people trip up. And so if I can get rid of minus signs, I do. If we identify which of these torques are trying to make it go clockwise and put them on the left of the equal sign, and which of them are trying to make it go counterclockwise, put them on the right side of the equal sign, there will never, I repeat, there will never ever be a minus sign in your equation. None. If you see one, you know you've made a mistake. Okay? Now, if I want to balance this beam about this pivot point, I have to identify which are clockwise and which are counterclockwise. Well, if this beam were forced to rotate like this were a hinge, this weight would be trying to make it go clockwise. This spring scale is pulling up, trying to make it go counterclockwise. And so that means that this spring scale must be pulling with 800 newtons. Why? Because 800 times a quarter gives me 200 meter newtons. 200 times a meter gives me 200 meter newtons. The clockwise torque balances the counterclockwise torque. Okay? Now, last day, right at the end, really, really quick, we solved this problem. You remember that we've got this beam that has a mass of 1 kilogram and a length of 1 meter. And we hang from the 80 centimeter mark 1 kilogram mass. And we wanted to predict the reading on these two scales. Well, the fact that the acceleration of that bar is 0 tells me that all the force up has to balance all the force down. I've got 20 newtons pulling down, 10 from the weight of the bar and 10 from this tension right here. So that means the two spring scales have to pull up with 20 newtons. But I don't know how that divides up. So now I use the fact that there's no angular acceleration and balance the torques. Well, I'm looking for these tension forces. The poles are on that bar. So I draw a free body diagram, an extended free body diagram. I don't draw it as a dot because I care where the forces are applied. The first force I put on any diagram is the weight force, and I always, every stinking time, put it at the center of mass. I then ask what else is touching that bar. Well, I've got the string pulling down 80 centimeters from the left, and I have the two spring scales pulling up. Now, again, I explained this last day. This bar is not rotating about any point in the universe. And so mathematically, I can pick any point as my pivot point. But there are only two smart choices if I don't want to do messy math. I've got two unknowns, and I can't solve one equation with two unknowns. I have to get rid of one of those. Well, if I choose my pivot here, the torque due to the left tension goes away. It's 0 because I'm pushing at the hinge. If you push at the hinge of that door, it doesn't open, okay? If I choose my pivot point here, I eliminate this unknown, T sub r, because it's acting at the hinge. Now, I chose last day to put the pivot here and solve the problem. You remember we went through the solution, but essentially I just identified which of these forces were trying to make it go clockwise and which were trying to make it go counterclockwise. If it's forced to rotate about that point, like you've driven some spike through there, this is trying to make the bar go clockwise, counterclockwise. And so my equation looks like this. This force times its distance to the pivot plus this force times its distance to the pivot. Those are the clockwise torques. They have to balance this force times its distance to the pivot. And I get 13 newtons. It's all got to add up to 20, so the other one must be 7. And when we uncover the spring scales, what I have is 7 and a little bit, and 13 and a little bit, and we need to spend more of your tuition money on spring scales. I tell you, I went through 8 spring scales, and these were the closest ones to accurate that we've got. There's got to be better spring scales. But really quick, I want to solve this again, but this time I'm going to put the pivot over here, okay? And just show you that you get the same answer as long as you do the problem correctly. If I use the fact that clockwise torque has to balance counterclockwise torque, and I pretend that the bar has to rotate about that hinge, this is going to give me 0 torque. It's acting right at the pivot. This is going to try to make it go counterclockwise, counterclockwise. This one's trying to make it go clockwise. So again, my formula looks like this. The only clockwise torque is this force, unknown, times its distance to the pivot. The 2 counterclockwise ones, I've got the weight with its distance to the pivot, and I've got the hanging mass, the tension force, times its distance to the pivot. If I solve that for the unknown, I get 7 newtons. Again, it's got to add up to 20, so the other one is 13. Check on your neighbor, see if your neighbor finds that trivial.
Yeah, it's
Class isn't over, Brimley.
Think of it as
yeah. No, that's
on one of those.
Are there questions?
first thought I was like, now the big is
Okay. Let's look at one of your homework problems. You've got Will and Bob, and they're brothers, and there are a lot of Will and Bob problems in the textbook. And it turns out that Will is always slacking off. He's just never doing as much work as Bob there. Well, the brothers have figured out a very clever way of taking their lunchbox to work. They do it by attaching it to a 71 kilogram beam and then hauling that beam around. And they found that no one steals their lunchbox. So the question is, how hard is Bob pushing on that beam? And how hard is Will pushing on that beam? Okay. Now they're pushing on the beam. So those are forces on the beam. So the first thing I do is draw an extended free body diagram of the beam. And the first force I put on any diagram is the weight force. I always put it at the center of mass. And then I ask, are there any other non-contact forces? Any magnets? No. So what touches the beam? Well, I've got that tension force from the lunch, and then I have Will and Bob pushing up. Now again, the beam's not rotating about any point. I can choose any point as my pivot and balance the torques. But the 2 smart places to choose the pivot are here to eliminate the force by Will, which is an unknown, or here to eliminate the unknown force by Bob. Now, if I choose my pivot over here and balance all the clockwise torque with all the counterclockwise torque, again, the most important step is figuring out which are clockwise and which are counterclockwise. Pretend that there's a spike through that X, forcing the beam to rotate about that X. This force, if it were the only one acting, would try to make it go clockwise. This one would try to make it go counterclockwise. This one would try to make it go clockwise. So I set up my equation, the clockwise torques. I've got the weight force times its distance to the pivot. And we were told in the problem that the beam was 2 meters long. I didn't put that on the slide. That's my fault. But in your homework problem, you were told that this was 2 meters long. So this is, well, I guess I did show it right here. Okay. So then you have this force by the tension in the rope times its distance to the pivot. Now, I'm an old man, and I wish I had a happier story to tell you. But this was on an exam years ago, and a whole bunch of my class missed it because they used this distance here instead of that distance there. Because I had put it on the diagram. Is that wrong or sick and wrong? That's sick and wrong. That's sick and wrong. What you want is the distance to the pivot, not the distance that's labeled on the picture. Okay? That makes sense? And so when I solve that for the unknown force by Bob, I get 793 newtons. Well, the old rules still apply. All the force up has to balance all the force down. And I've got 710 newtons plus 200 newtons down. That's 910. Well, that means that Will's pushing with only 117 newtons, because 117 plus 793 gives me the 910 that I need to balance. Check again with your neighbor, please.
Big thing.
What I hope you are seeing is that Greg is going through the same recipe with each of these problems, that it's just step by step by step. And so even though I can throw a problem at you that looks like you've never seen anything like that before, they're all the same.
So
Okay, you draw your extended free body diagram, you choose a pivot to eliminate one of the unknowns, and then you decide which of the torques are clockwise, which are counterclockwise, and balance them. Okay, let's try this problem. This is also from an old exam. It turns out that we have a special meter stick. This happens to be 1 meter long. And if we hang a 1 kilogram rock from the 0 centimeter mark, we find that we can balance it right at the 25 centimeter mark. And it balances perfectly, perfectly. And so the question is, what is the mass of that special meter stick to make this happen? With your neighbor, find me a number. Find me a number.
Chris, what your
Well, it has to be the same on both sides.
yeah, split it.
So if you have a 1 kilogram rock, you have the same amount of meters on both sides. If you cut out the meter stick each side, then just think about only half.
Then
the
we have
meter stick
one,
sides.
Yeah,
And
I
you
got
want that.
saying.
That's 1 kilogram and the rest. Yeah.
When you find your answer, tell me whether your answer is less than 1 kilogram, equal to 1 kilogram, or more than 1 kilogram. The answers are going to be all over the map, and we can bin them into these 3 categories. So just tell me
Far away it is.
which category your answer falls in.
Yeah,
Hey,
you know what?
in-
No, you're right. You're right. No, you're right. It works well. I know it.
Look at the rocks.
So we have,
like
I think we have to
close
think about, we have to think about torque.
Yeah.
I think it might be.
My initial thought was thinking. Between. Fulcum, yeah. It's like. Down, that's like the center of. That might have been.
Is that a third?
Yeah, I think we have to think about four.
Where the 1 kilogram rock is sitting.
So when we, the mass use I can't remember what you call it,
Yeah.
the whatever, the side.
Center the one that I was forgetting.
So we can be the amount of distance, we'll just say that it was.
I see what you're saying.
Four
Yes,
X.
4.
You take a bite, take a bite.
Now.
Something, how much if you live?
3. So there's 4.
Kind of confused with that, you know.
See.
Okay, get your answer in, please.
Read.
What was that? So 1.5.
Sure.
There's the way you did it.
So.
It was like you say 5.
Last call?
I've got a good.
That would make more sense. Yeah.
Okay, the winner is greater than 1 kilogram. Let's talk about that.
Really curious to this.
Let's solve this problem together. Oh, it's already been solved. I'm so sorry.
So, what are,
We don't know what this.
Okay,
Certain that.
because
we are looking for forces on that meter stick. Well, actually, Greg, I'm looking for the mass of that meter stick. But the mass of that meter stick is related to the weight force on that meter stick. The weight force is just the mass of the meter stick times G. So if I can find this force, I can find quickly the mass. Well, anytime you're looking for a force, any force, you draw an extended free body diagram. And the first force you put on any diagram, free body diagram, is the weight force. And you always put that at the center of mass. Now, some of you are screaming inside of your head, but Greg, part of that meter stick is on the right of the pivot and part of it's on the left. And I assure you, the Earth don't care what it's doing. The Earth pulls on that meter stick the same whether it's on the pivot or not on the pivot. And it always pulls, you can show mathematically, as if it were all being pulled at the center of mass. Okay? Now, I ask, what other forces do I have? Well, I've got this tension force due to the hanging rock on the meter stick, and I know that that's 10 newtons. Okay? I also know that there's this normal force by the pivot on the meter stick acting right here. Well, I've got two unknown forces, and I can't solve for two unknowns with only one equation. And so that's why I want to use the idea of torque, because I can get rid of one of those unknowns by choosing my pivot to be right here. Well, Greg, that is the pivot. You just labeled it as a pivot. Well, yes, but that's not why I'm choosing it as my pivot point. this thing's not rotating at the moment. And so I can balance my torques about any point, including a point in Kansas. I choose this point as my pivot point to get rid of this unknown that I don't care about, because I'm trying to find this unknown here. So I choose it for practical reasons, for mathematical reasons, not because it's the pivot, okay? Now, if I identify which torques are clockwise and counterclockwise, the weight force is trying to make this thing rotate clockwise. The tension force is trying to make it go counterclockwise. So I would say the weight force on the meter stick times its lever arm of 0.25 meters, 25 centimeters, has to equal the tension force of 10 newtons times its lever arm of 0.25 meters. And since I've got the same lever arm for both of those forces, that means that the weight force on the meter stick has to be 10 newtons. And that means that the mass of the meter stick has to be 1 kilogram. Okay? See if your neighbor got that right. If not, slap them hard in the face.
Yeah, I got it.
Exact same.
I think he just didn't say, oh.
Okay. Now, for those in the room that are unbelievers, that are just not buying this, I suggest an activity. If you want to prove that this is true, what you should do is divide up this meter stick into two parts, a left part and a right part. And then treat it as two sticks that are glued together right here.
Yes.
Now, the center of mass for the left part would be right here at 12.5 centimeters. This would be the weight of the left. And the center of mass over here, this would be the weight of the right. And the weight of the left plus the weight of the right are going to add up to the total weight of the meter stick. If you solve that again, balancing left torque and right torque, or I'm sorry, clockwise torque and counterclockwise torque, you're going to have to solve two equations and two unknowns. It's going to be messy, but you will get the exact same answer. You will find that it has a mass of 1 kilogram. Questions? Concerns? Okay. Let's turn our attention now to some new material. Whoops. My bad. Old people, what are you going to do? Okay. Research has shown that one of the least effective ways of teaching is just by analogy. It just doesn't sink in as deep. And yet, teaching by analogy is a very, very quick way of getting ideas across. And frankly, people, we're running out of semester. Okay, so these last two ideas that I think you need, I'm going to teach by analogy and hope that we can make it stick. When we were studying linear motion of the center of mass, we found that the one equation that solved more than anything else, the one equation to rule them all and in the darkness bind them, was Newton's second law, that the net force caused a mass to accelerate. And in particular, it was just that center of mass of that object that this equation applied to. Well, if we look at the rotational analog, we found last day that a torque, a net torque, caused an angular acceleration. So we hope that there's some sort of relationship that looks like the linear one, okay? And the question is the mass the proper constant of proportionality? Is it just identical to what we have in the linear case? Now, to address that, we're going to do an event that I call the rotating rods, a new Olympic event, and we need some help here. Would you help me today? Would you help me today? Okay, come on down. Help me with names again. Written? Oh, great. Oh, I keep choosing great. And Mary. My mother's name was Mary. Yeah, my granddaughter's name is Mary. Okay, this is the way we compete. Each of them is going to hold one of these in their right hand. And when I say go, they're going to try to rotate it just as fast as they can, back and forth like that. And the one that can do it the fastest is the winner. Okay, so face the class. Hold it in the middle. Ready, set, go.
Shoot, I thought it'd be fast.
Okay, I don't know. It looks like Mary's beating you great. Okay, now, you know that these things are rigged, right? Okay, let's do that again. Ready, set, go. Okay, now. I should have never chosen great. He's really great. Okay, stop. Okay, let's give him a hand, folks. I should have told you at the beginning, I just forgot, that these are identical in mass. If I put them on a scale, they would read exactly the same thing. But you saw that when Mary had this one, she was struggling to get it to go around. Whereas when she had this one, she was able to go really fast. Britton was able to go fast with either one, but he's not human. Okay. So the difference is they have the same mass, but for this red one, all the mass is located right in the middle, close to the center where the axis of rotation is located. Whereas on the blue one, the mass is out at the ends, far away from the rotation axis, and that makes it harder to rotate. Now, what we just proved with that little exercise is that it can't be the mass, because they had the same mass, but one of them took a bigger torque to get the same acceleration. So if they had the same mass and this were the right equation, they should both need the same torque to get the same acceleration. So it has to be something more complicated. Now it turns out that something we give the symbol capital I to, and we call it the moment of inertia. And that has nothing to do with time. Moment is a word from calculus that essentially refers to an integral. We don't care about that. This is not a calculus-based class, okay? That's just a name. But you'll notice that this depends on the mass, but also on the size. And this dependence on the size is squared, so that's an important dependency. And then there's this constant, B, which is different for every shape. Now, in textbooks, in introductory physics textbooks, you'll always find this diagram. And don't let this scare you. You will not need this diagram, okay? You will not need this. But I just want to point out that different shapes have different values for B. A disk has the value of 1/2, whereas a ring has a value of 1. If I have a solid sphere, like a bowling ball or a billiard ball, the value of B is 2/5. But if my ball is hollow, like a beach ball, it would be 2/3, okay? I had to memorize these for all the different shapes when I was your age. And it has not helped me in my parenting one bit, okay? I have rarely found this useful. And the few times that I needed this information, I knew exactly where to find it in my book. Okay, so don't be memorizing this table. But I hope it makes sense. I hope it makes sense. With a disk, some of the mass is located close to the axis of rotation. Whereas with a ring, all of the mass is out far from the axis of rotation. And so I get a bigger value for B, a bigger moment of inertia. Remember, moment of inertia is how hard it is to get something rotating, okay? Likewise, with a solid sphere like a billiard ball, some of that mass is close to the center of the ball, close to the center of the axis of rotation. But with a hollow ball, like a beach ball, more of that mass is out further away from the axis of rotation. And so I get a bigger value for the hollow ball than for the solid ball. See if your neighbor is making sense of that.
Actually wasn't
Now,
a semester, but then I switched.
you would never be asked on an exam to calculate a moment of inertia or use the moment of inertia to solve a numerical problem. It's more like the sample exam where you've got a frog on a rotating disc, and as he jumps towards the center, you know, what does that do to the moment of inertia? It's just, does it get bigger? Does it get smaller? That sort of thing. Okay. Let's talk about this in some real life examples, like going to the circus. If you go to the circus, there's usually a high wire act, and there's some performer up there walking along that wire. And if they're really experienced, they're just doing it like this, okay? If they're not so experienced, if they're new at the job, they've got a really long bar that they're holding in the middle as they go across the wire. And if it's their first day on the job, they've got a long bar with heavy weights at both ends. And those heavy weights give this bar a huge moment of inertia, making it very, very hard to rotate. And so as they go along this wire, if they tip or if they slip, they just pull themselves up. It's like this is stapled to the sky. It's like they've got training wheels, okay? And they can just pull themselves back up and go on their way. Now, we've got another demo here. Come on down.
Okay.
Grant.
Yeah.
Jackson.
Yeah.
Jackson Grant. Come on down, Jackson. Okay. What Jackson's going to do is he's going to balance this on his finger like this, and then he's going to balance in it like that and tell us which way is easier. Okay.
Really don't know. Maybe this is harder.
Yeah.
Okay.
Yeah.
Okay.
Give him a hand, folks. When the mass is further away from the axis of rotation, his finger, the moment of inertia is bigger. That means it takes more torque to make it rotate. And that means it's easier to balance. Now, at that same circus, there's usually a group of performers, they're brothers, the Linguini brothers, okay? And the oldest Linguini brother puts the youngest brother in a chair on top of a 20-foot pole. And then he hoists that chair with his brother on it and balances it on his forehead, knowing that if he drops his little brother, his mother is going to be really upset with him, okay? And the fact that this pole is 20 feet long makes it look really scary. But the fact that the pole is 20 feet long makes it easier for the older Linguini brother to balance his brother. With that mass so far away from the axis of rotation, the moment of inertia is huge, and it's very hard to rotate that object. See if your neighbor's following that logic.
Yeah. Here's a. Here's how we do it. I've been good at it. Light.
It's not that bad.
Oh, Jackson, you get another cookie for that. Yeah. Okay. Okay. New topic. The last topic. The last topic of Physics 105. Yes, we made it. When we were talking about linear motion, we found that if we could isolate a system so that all of the external forces add up to zero, that there was something called momentum, linear momentum, that was conserved, that stayed the same, regardless of how messy the situation became. And that linear momentum was just the mass times the velocity. And the momentum and the velocity are vectors in the same direction, okay? And the vector nature is very important there, we found. Well, again, by analogy, which is not the best way to teach, we find that if we can isolate a system so that all of the external torques add up to zero, that there's something that's conserved called angular momentum. Now, linear momentum is mass times linear velocity. What do you suppose angular momentum is? Well, instead of linear velocity, I expect that I'm going to have angular velocity. And instead of linear mass, I guess we don't usually call it linear mass, but mass is just how hard it is to get something moving in a straight line. Moment of inertia is how hard it is to get something rotating. And so I replace mass with moment of inertia. I replace linear velocity with angular velocity. And again, these things are vectors. Angular momentum's a vector, and angular velocity is a vector, and they're in the same direction. Now, I can demonstrate that with a gyroscope. And this gyroscope has been balanced. Oh, it was balanced this morning. Okay, I'm unhappy. Someone's been messing with my, oh, my bad. It was balanced and I just unbalanced it. Close enough. Okay, I'm going to spin this up and again, I had a nice bowline on here this morning and someone took it off. Boy Scout knots to the rescue. There we go. Okay. And now I have to be careful here. I'm going to pull on this string really hard. And one semester in Montana, I pulled on it and a student right there just fell out of their seat because I just snapped them in the forehead. That didn't end well. You ready? Okay. Once I establish an angular momentum, as long as the torques are balanced, that angular momentum stays constant. The spin rate is going to stay constant in this case, and also the direction. The omega by right-hand rule is right out this axis here. And so if I pick up the base and move that around, the spinning disc always has the same axis of rotation. Okay. Do a little dance. Make a little. Okay. Now, those of you in ROTC, what could I do with that? I'll give you a hint. If I had 3 of them in the cone of a missile, one of them pointing east, one of them pointing north, and one of them pointing up away from the center of the earth. As that missile was traveling, it would always know where east was and where north was and where up was. And that means it could follow a digital map down the canyon and around this corner and Osama bin Laden. Yeah. Thanks, Obama. Okay. Yeah. Now, so let me show you another demonstration of this. If I spin up this wheel, oh, I got it against something. My bad. I can't hold it much longer, Captain. Okay, now this has an angular momentum by right-hand rule that's pointing towards the ceiling. If I isolate myself from all torque with this rotating seat with good bearings, the angular momentum of me and the wheel is towards the ceiling. If I force the angular momentum of the wheel to point towards the floor, my angular momentum has to be towards the ceiling so that the total angular momentum of the system, me and the wheel, is still towards the ceiling. And then I can stop or I can turn. This is how you turn a spy satellite in space. Oh, there's Russia. Oh, there's Canada, our other enemy. Just so you know, if we ever go to war with Canada, I'm Canadian, eh? I was born in Provo, but I'm Canadian. I love those people. They're so nice. Okay. Now, there's a wrinkle. First of all, before I show you the wrinkle, if I get rid of the balance over here by hanging this weight, you see that it precesses, which is what we saw with the wheel last day. The torques have to be balanced in order for the angular momentum to be conserved. Now, the big difference between linear momentum and angular momentum is that I can't change my mass quickly, okay? That's diet or exercise. And so once I get something in outer space with a certain velocity, it just keeps going forever. On the other hand, I can change my moment of inertia, okay? If you think of a skater, a figure skater, they always go into their turn like this, only a little more gracefully, okay? And as soon as they establish their spin rate, they pull in their arms and their legs so that they go really fast. Now, I can demonstrate that again with this chair. Don't want to. Okay, I need someone to come and spin me up. Thank you. Just spin me and get out of the way. Whoa, okay. Thank you. Let's give him a hand. So you people stop moving. Stop moving. Whoa, you're going all around. So, I have a story that I'm not proud of. When we were in student housing at MIT, it turns out there were only two types of families there. One family type was international from all over the world with their children. And the other type were Americans that were members of the Church of Jesus Christ of Latter-day Saints with their children. There were no American citizens who were not LDS who had children in the housing complex. So our kids grew up on a playground where they heard all different languages, and it was a wonderful experience. One day, it happened to be Thanksgiving, and I was home with my children, and I was with the two older children and their friend on we had this tire swing, and it was a horizontal tire with chains that went up and it could rotate. And my kids liked to play a game where they would lean out as far as they could all the way around this wheel, and I would get them spinning and then say, 1, 2, 3, now, and then all pull in and spin really quick till they puke. You know, it was a really fun thing. So I'm out there with two of my kids and their friend, and we're about to play the game, and this big kid comes up. Could I play? And my son and daughter are like, that's him. He was the bully, the one that they were afraid of, and the ones that they were always avoiding. And so I said, sure, hop on. And my kids are, Dad, what? Let's play the game. So we all lean out. I get them spinning faster than they've ever been going before. Remember, 3 of them know the rules, and 1 of them doesn't. And I say, 1, 2, 3, now. And they all go up, and he just, ah. So I ask, who's the bully? Yeah, I'm sorry. Okay. Let's go back and practice some of these torque problems. This is the type of problem that you hope is on your last exam, okay? It's just straightforward. All of the torques are the easy kind where the force is perpendicular to the position vector. In this problem, you've got a platform with a mass of 40 kilograms. A painter is on that platform. He has a mass of 70 kilograms. And we want to know the tension in those two cables. Now, those tension forces are acting on the platform. So I want to draw an extended free body diagram for the platform. The first force I put on there is the 400 Newton weight force, again in the center of mass. I then ask what other forces act. Well, the painter's pushing down with a normal force equal to his weight force because he has no acceleration. And then I have the two tension forces. Again, physically, I'm able to choose any pivot point anywhere and get the right answer. But there's only 2 smart places to choose my pivot point. If I choose it here, I eliminate this tension force from my equation. If I put it here, I eliminate this tension force from my equation. I'm going to put my pivot point here and balance the clockwise torque with the counterclockwise torque. if I pretend that there's a spike going through that X, forcing this platform to rotate about that spike, this force is trying to make it go clockwise. This one's trying to make it go clockwise. This one's trying to make it go counterclockwise. And so my equation looks like this. I've got the 400 Newton weight times its distance to the pivot. I have the 700 Newton normal force by the painter times its distance to the pivot. And then in the counterclockwise direction, I have the unknown tension in the right cable times its distance to the pivot. When I solve that for the tension in the right cable, I get 600 Newtons. Well, all the force up has to balance all the force down. I've got 1100 Newtons down, 400 and 700 makes 1100. And that means I have to have 1100 Newtons up. So this has to be 500 Newtons, okay? See if your neighbor finds that trivial.
That wants to like choose a new
Okay,
that pivot.
questions on that one?
That's like, that's what he was saying, you can't.
Is that a hand up? Nope, just stretching? Okay.
But yeah, I do.
This is the type of problem you hope is not on your exam. Okay. This is another homework problem. In this problem, we have a drawbridge that is 24 meters long with a mass of 2,000 kilograms, and it's being held up at an angle of 53 degrees by two cables, each one on each side of the drawbridge, and they each have a tension T, which is what we're looking for. What is that tension force? Now, that tension is acting on the drawbridge, and so I'm going to draw an extended free body diagram for the drawbridge. The first force I put on any diagram is the weight force. For 2,000 kilograms, that would be 20,000 newtons, and it points straight down towards the center of the earth. I then ask what touches that drawbridge. Well, I've got the two cables, one on each side, pulling with tension T. And then I have all sorts of forces right at that pivot point, at that hinge right there. And those forces I don't know anything about. And more importantly, I don't want to know anything about. I'm not offered any points in the homework for that information. I've been asked about these tension forces. So I'm going to balance the torques about this pivot point right there. Again, Greg, that's where it pivots. When you lower that drawbridge, that's where it rotates from, okay? But here's the thing. This is an old castle. That drawbridge hasn't been lowered for 200 years. It's all rusted over. It's never going down again, okay? Now, what that means is that I chose this as my pivot point for mathematical reasons, for practical reasons. I want to get rid of these forces right here in my equation. And so that's why I choose that pivot point right there. Now, this is different than the last problem because these forces are perpendicular to their position vectors, but this one is not. This is one of those 5% problems where I don't have a force perpendicular to the distance to the pivot. And so now I have to choose one of those three methods. Well, I choose the useful force method, and I'm going to break up that weight force into two parts, a part that's perpendicular to the drawbridge and a part that's parallel to the drawbridge. Now I've drawn them like this so that I could use some trig and some geometry, but in truth, these arrows, the green one and the blue one, represent forces that are acting right there at the center of mass. And so this green force is pulling right down through the pivot point. And so this is going to give me 0 torque about that pivot point. It's only this perpendicular part of the weight that's going to give me a torque. Now, I know from what we've done in the past that this angle has to be the same as the angle of the drawbridge. Okay, remember the spike through the board. And so I can use my trig right now. If I know the hypotenuse is 20,000, that's going to give me 12,000 newtons for this part here. I've used the cosine of 53 degrees. Now, if I look for which forces are giving me a clockwise torque and which are giving me a counterclockwise torque, again, I pretend there's a spike through there, and this one's trying to make it go clockwise. These two are trying to make it go counterclockwise. So my equation looks like this. There's the 12,000 newtons times its distance to the pivot. If the drawbridge was 24 meters long, this distance to the center of mass would be 12 meters. And then I've got this tension force times its distance to the pivot. We were told that's 8 meters, and there's 2 of them. When I solve that for the tension, I get 9,000 newtons. See if your neighbor followed that. See if they were able to understand that. Questions? Yes, sir. Just a second. Let me come back there. Batman running. Oh, that was given in the problem. If we go back,
This is the beginning of it.
Oh, yes, the 2 is equals the 2 tension.
Follow that.
the 8 meters. Okay. Other questions? On Tuesday next week. Oh, yes. Great.
You know, it's your.
Really, people? You waited this long to tell the man that can't hear that this been grinding on your eardrums that whole time? You gotta speak up. You gotta say, Francis, it's still going. Thank you, belatedly. Okay. Taking 12 points away from everyone. Yeah, no, I'm not. On Tuesday of next week, I'm going to start with a rotational kinematics problem from an old exam. I'm going to then move to 2 buoyancy problems from old exams. And then I'm going to do 4 different torque problems from old exams. Okay, I'm just going to go through problem after problem after problem. There will not be any reading assignment for Tuesday. There will be no clicker points on Tuesday. Today was the last day that we had clicker points. So if you're still hungry, come get yourself another cookie while they last. Hey, good brother. Let me turn off the recording real quick.
But okay, let's go to the next class.
See ya.
That's great.
Especially like the fact that you guys can't take it.
Good luck. See you later.